Hello everyone, welcome to your next section. Today we're going to be talking about this concept called deep learning, which is kind of a hot new area of data science. Well, it's getting a little bit older now, but a couple years ago this was the sexiest stuff on the planet, and now you're starting to see artificial intelligence using these deep learning models for a lot more things these days. So deep learning is a really interesting concept. It's a lot more sophisticated than a lot of the machine learning algorithms that you have encountered or probably would encounter. A lot of people do seem to separate machine learning from deep learning for that reason, because it's almost a completely different world in terms of the things that you have to do. But that in mind, it really is a type of machine learning. So what you're going to learn today is what is the difference between machine learning and deep learning. We're going to talk about the basics of deep learning by introducing you to how neurons work and like the basics of some psychology. And we're going to talk about the concept of an artificial neural network as the output or the byproduct of all of this knowledge, okay? So why don't we just start talking about deep learning and see how we do this, guys. So first off, what is deep learning? It really is a type of machine learning, but rather than modeling it off a process like we learned about with decision trees or a support vector machine or some sort of association algorithm, deep learning is built, the framework of deep learning is based around how we think the brain works, or at least a simplified framework of how neurons, interconnected sets of neurons can learn patterns from example, okay? So deep learning models are really good at unsupervised problems where we don't have a really good sense of like how the pattern of behavior is operating, and if we expect that the behaviors are changing over time or at any given point, deep learning is a really interesting way of trying to get an algorithm to learn those differentiations. So deep learning has applications that are general, but it can be very specific because there's some things you can't do with, let's say, a random forest that you might actually be able to do with deep learning. For instance, like you know, some sort of live time series based decision can be done much better with deep learning, perhaps, than some machine learning models. So let's talk about some definitions. In order to build an artificial neural network, you have an input layer, and this is a set of input responses, almost like a list of variables, and this is the observational information that you teach the neural network. The input layer connects to a set of hidden layers. You can think of these like layers of neurons, and I'll tell you what a neuron is in a moment. These neurons are kind of like the cells in our brain that receive electrical input. So they're receiving information from this input layer, they activate in a certain way, and then they pass that activation off into another layer in the network. And what you would expect to find at the end of all of that passing off of activation is that the final output layer, hopefully, the purpose of the final output layer is that one neuron activates, giving you your classification or your decision or whatever type of response you're expecting your neural network to be. Okay, so in terms of syntax, guys, we're gonna hop into our normal thing, but there's no like you know, graph that I'm going to show you. I'm actually going to draw some of this out for you, okay? And then we're going to look at some examples of how neural networks work from a fantastic web page. So first off, a neuron kind of looks like this, guys. If this is the cell body of a neuron, it has these it has this thing called an axon, which is, you know, it sends information out to other neurons, and then it has these things called dendrites, which, you know, touch other neurons in the network, okay? So this is the cell body, like the neuron proper. This is an axon, and these are dendrites. And how the brain works is we have millions and millions of these, probably billions actually, and they're all interconnected to each other through axons and dendrites. And how this all happens is that if some information comes into this neuron here, this thing might activate. And if it activates, it is basically just passing electrical signal through its axon into another neuron in many different places. Now, the connections between neurons are many to many, so you can have this one neuron activating other neurons. But because of how, you know, electricity works and how, we have things like energy is in a perpetual motion machine. We lose some activation as this passes through an axon into another neuron. So the cascade of activation needs to occur from a bunch of neurons in a bunch of places, and hopefully sets of networks or sets of neurons activate all the way down the chain until we have some sort of classification, okay? So that is all you really need to understand about neurons. Essentially, they're just like a cell that can receive information in current, and if it's a certain type of current or a certain information from a certain area, it will activate or inhibit, okay? How artificial neural networks work is that you have your hidden layer, which is just basically your data, or not your hidden layer, your input layer. I'm going to call this II. And each of these, let's just say there are 3 pieces of data in this input layer, and then we had, for our first node, let's say like 5, for our first hidden layer, 5 neurons. And we actually use the language neurons when we talk about artificial neural networks. So these 3 pieces of information should touch every single neuron. So we want this piece of information to activate every single neuron in this hidden layer. And we would expect that the activations are different based on each neuron's sensitivity. So if the sum of all these activations for this piece of data was 1.0, we would have a distribution, let's say 0.8, and this is like 0.05, or let's do 7. It's a little easier for my brain. Let's fix that. There we go. So the activation for this neuron here is 0.7, this one here is 0.1, this one here is 0.1, this is 0.05, and 0.05. So the sum of activations for any given piece of data should be 1. And you have these interconnected sets all the way through as well. And they all activate all at different points. And so once you have all these activations, let's say let's connect all these. Let's say this neuron, the sum of the activations for this neuron is 5, and 2, 4, 1, and like 0.3, okay? Or 0.5. That would mean that, at least in this hidden layer, this neuron activated maximally. So maybe we should strengthen the connections between all of these pieces of data and this neuron. You can have many hidden layers stacked upon each other. So that's why hidden layers, like we kind of use that in the plural. I'm just going to add 3 here. Let's also say that this piece of data is like an image, all right? And that we're trying to determine if it's a cat or a tree. This activation was very high here, but all of these hidden layers also connect to each other. And the sum of the activations for each of these things tells us, what we hope is that this artificial neural network starts to learn patterns between things based on these sets of interconnected layers, okay? Eventually, if we have, what we'd end up having, so this is our hidden layer here, and depending on how many layers, people talk about all the size of each layer and how many they go deep, the differences between hidden layers across the network. All of these things are points of great discussion and debate within neural networks. But for instance, for our demonstration, at the very end of this, we want to know if this is a cat or a tree, so we create an output layer with one of 2 decisions. And let's just do that, and that. And based on this activation, we can do training and testing algorithms with k-fold validation. Remember, I told you all about that. And what that can do is determine like how accurate our artificial neural network is determining between cats and dogs if we had labels, or sorry, cats and trees if we had labels for these images and the networks therein. Okay, so that's basically how a neural network works. You have an input layer that activates a set of neurons. Those neurons pass on their activation to other neurons, either in greater layer size or less layer size, and over and over again, and eventually they get passed out to an output layer where we determine, did this actively classify or accurately classify what we wanted it to? If it didn't, we adjust all the weights, let's say we would weaken the weights from this guy here, and let's say this activated the most. We'd weaken these weights and strengthen the others. If it was accurate, we would strengthen this weight even more and weaken these. Does that make sense? So that is basically how an artificial neural network works, and it has multiple iterations. So it passes through this once, makes its corrections, goes again, and we call that iterative process epochs. And essentially, this is the basics of neural networks. How these things get activated is another area that we could spend a whole class on. How we decide neuron sizes or hidden layer sizes and what output should be, that's a fine art as well. But fundamentally, that's what's going on here, okay? So we're going to go into a website now, and we're going to play around with this. Go to playground.tensorflow.org, and this is going to show you demos of artificial neural networks. So first off, what this is showing is what features are we looking to use to try and determine our classification. You'll actually probably recognize this example here, guys. This is the example I use for support vector machines, where you have a cluster of data that looks like this, and you have yellow and or orange and blue, and you're trying to like create a line that distinguishes between these two. So what you're going to see here first is the top bar. It's going to tell you play, pause, and there's a certain amount of epochs. We're telling it the learning rate, how hard we want it to learn in that back and forward process. This thing called activation is how we activate each of the neurons in our hidden layers. Regularization is something you don't need to know, and we're looking at a classification problem for this example. But you guys can play with this as much as you want. You can also look at the different data types that you can use for it to learn. Let's try and get it to learn this one instead, since this is a more interesting example than what we've seen. And we're going to use these two features here to try and classify it. We can also use, these are like basically different properties that we can hint at. We can tell it, you know, you should expect your X parameter, like, you know, manipulate your X parameters a little bit, and it will change the way it's like attacking its learning. We then have, so we have like, you know, two labels here that it can learn on. We then have 4 neurons that have been specially trained to like learn specific patterns. And then we have our output, which is our classification between blue and yellow. Okay, so if we just run this as is, let's see what happens. Over time, this thing starts to learn the differences between these two things. You'll notice at first, let's run this one more. Ooh, let's run this again. The first thing it learned was it learns that, let's pause. Oop, oop, oop. It learns basically that yellow is kind of diagonal across. And then over time starts to disambiguate that maybe actually blue is in the middle here. Well, this took 80 epochs, 80 different sets of training routines for this to work. And over time, as you give it more and more chances to learn, it can figure out that these different blotches exist. And this is not something that you could just like give a linear regression or a specific shaped algorithm or statistical analysis tool, to figure out something like this. What happens if we increase our hidden layers? Let's add 6 neurons here and 3 neurons and then down. Let's see how fast this learns this time. Okay, so it actually learned a lot faster, but it also learned a little bit different things as well, that this boundary here is still for orange. So this set of hidden layers was able to learn something slightly different. So this is the interesting thing about artificial neural networks that makes them both a plus and a minus, is that because they're very good at being adaptable, these layers, it's not exactly always clear how these hidden layers are learning things. And they tend to learn things in slightly different ways if you adjust the parameters ever so slightly. So the problem is that we don't ever know if a deep learning algorithm learned what we wanted it to, at least out of the box. So when we do deep learning these days, a lot of time and effort is being spent on trying to figure out if we can interpret learning from neural networks. That's all I really wanted to show you for neural nets, guys. Play with this a lot more, increase the learning rate, change the data type, adjust your training and test, your k-fold validation, adjust the amount of noise, how many batches you want it to make examples of before it goes back and does its learning and reducing and increasing activations. And see for yourself, because this is a fantastic way of visually representing how neural nets are working. Okay guys, let's do a recap. We learned the basics of deep learning. We also learned the basics of like psychology and neuroscience, how a neuron works and some terms around that, and how that framework is the basics, or the simplest way that we model artificial neural networks. It's taking a lot of learning from neuroscience and psychology and trying to automate that process in computer science. So it's an interesting area. We're not going to spend a lot of time coding. We're not going to spend any time coding it, obviously, because we're at recap, but hopefully in another class, maybe in next, if you could check another class from me, you'll see that there's a machine learning class, and I'll spend a lot more time talking about deep learning in that and machine learning in general. So thank you very much, guys, and catch you next time.